we've been talking about renormalization. I'd like to somehow finish these chapters on renormalization. The trouble is they go on forever in Schwartz's book. But in chapter 19, it's kind of a pity, actually. I think it would have been better if he had started in chapter 19 and erased 16, 17, and 18, because the treatment in 19 is more sensible. So let me say what the spirit of it is. We start out with this sort of a Lagrangian Rho zero, of course, is the dark energy density, or a counterterm to make the dark energy density finite. If the dark energy density indeed is the ground state energy of quantum field theory, it's unclear what dark energy is. Anyway, the idea is that we rewrite this. In other words, the normalization of the fields here, the fields are normalized in some crazy way here. E0 is some infinite number, M0 is infinite, Rho 0 is infinite. We're going to use these infinities to cancel the infinities with current perturbation theory. So we rewrite this thing as minus a quarter F mu nu, and what Schwartz does in this chapter is he drops R on the field, because the fields with zeros are the so-called bare fields. And I'm going to drop the R also on all of the quantities that are renormalized and finite. Okay. So I'm going to write this a little bit differently from the way he wrote it. I psi bar d slash psi minus m psi bar psi minus e psi bar a slash psi. Okay, so this is this. Oh, he says, forget about Rho 0. We're not going to deal with that. That, of course, is the worst divergence of quantum field theory because it's quartic. But anyway, he says, all right, we're going to blow that away, and we're going to have these terms where these are the renormalized fields. This is the renormalized charge. So this E effectively should be the E that Coulomb measured. This M is the mass that, who the hell measured the electron first? Whoever. And so forth. Then there are these extra things which are the counterterms. And this is minus delta 3 over 4 F mu nu, plus I delta 2 psi bar d slash psi, minus delta m plus delta 2 m psi bar psi, minus e delta 1 psi bar a slash psi. Okay. Now, what are these deltas? These deltas are infinite counterterms. There's 1, 2, 3, 4 of them. And how did they come about? Well, they came about by setting psi 0 equal to the square root of z2 psi, and we're saying z2 is 1 plus delta 2. A0, the bare field, is square root of z3 a mu, and so this is square root of 1 plus delta 3 a mu. So once you expand in terms of the deltas, you can forget the z's if you want. M0 is Zm times m, which is 1 plus delta m times m. M is the mass of the electron. E0 is ZE times E, which is 1 plus delta E, E. Okay. And let's see. It'll turn out that, or rather we can, let me see if I've got all these terms. We have delta 2, delta 3, delta M, and delta E. So 4 numbers. And it turns out that delta E is delta 1 minus delta 2 minus a half delta 3 plus order e to the 4th. I must say, I just wrote that down and now I don't remember quite why it comes about. All right, anyway, so let's just, let me see if I can recall what this seems to follow from a definition here. Oh yeah, it's just a definition. So I would take it as a definition, and so let's just leave it as a definition. Okay, now what's the idea? The idea is that if as we remove the cutoff, all the deltas go to infinity. On the other hand, here's what people who like renormalization say. The idea is that we have some cutoff. It can be epsilon. In other words, D is 4 minus epsilon. Epsilon we're going to take to 0, but we'll have these counter terms of the form 1 over epsilon. Or rather, when we do the integrations, we'll find that we have singularities of the form 1 over epsilon. Okay. And those are the divergences. Like all of the divergences be related to 1 over epsilon. This is in dimensional regularization. In Pauli-Villars, what we'll do is we'll just have a group cutoff, lambda. We'll be sending lambda to infinity. Okay. So now, but the spirit of this thing, which makes some sense, is the following. That suppose we say D is, well, how about 3.9? That's pretty close to 4. So 1 over epsilon then is 0.1. And now, what's E squared? Well, E squared over 4 pi is 1 over 137. So if we have something like E squared over epsilon, or E squared over 4 pi epsilon, this is basically 0.1. This is 1 over 130. I'm sorry, 1 over epsilon then is 10, because epsilon is point. Epsilon is point. Epsilon is 0.1. 1 over epsilon is 10. That's that. So this is like 1 over 14. So we can imagine expanding powers of E squared over epsilon. And so that's the spirit of the thing. And of course what's really happening is that we don't understand physics at short distances, and we need a better theory to do that. And in particular, we're not going to get anywhere near explaining this unless we have a better theory. All right. Okay, well, let's now go through some of the basic calculations, which will be essentially repeats of what was done in the earlier chapters, the ones I said could have erased. But in fact, there were calculations there. I think it would have been better to do those calculations in this scheme rather than to do them in the older scheme. All right. So let's look at what we're going to have is that these extra terms, these things are called counterterms. Counterterms. And counterterms is one word, actually, without a hyphen normally. And so what are these counterterms? Well, there are basically four different, in a sense, I guess we also call the deltas counterterms. Anyway, there are four different terms, and we can see them here. There's this one, there's that one, there's this one, and then that one. There are four different terms. And there's one, like we'll write this way. And this thing we're going to call I, P slash delta 2 minus delta M plus delta 2 times M. Maybe I should write this like that. Okay. So what did these were changes to the, let us say, the electron propagator. And so they would be, here you get delta 2 P slash. So that's this thing. And then on the other hand, we also have another psi bar psi term is delta M plus delta 2 times M. And that's this term. So this is one way in which the counterterms are going to occur. Then the photon line can have counterterms. We call this mu and nu. And we'd say this would be minus I delta 3 times P squared G mu nu minus P mu P nu. Okay. Now, where did this come from? Well, the delta 3 comes from the F mu nu term. And the F mu nu term, of course, has d mu a nu, so that's where the d mu's and the that's where the p's come from, the derivatives acting on the gauge field or the electromagnetic field. And after you've carried that out, and you find this term. There is a subtlety here, namely that in you remember when we did the Faddeev-Popov trick, and in fact something before the Faddeev-Popov, we did just the gauge fixing in quantum electrodynamics in the path integral formalism. And there we said, well, there's going to be a term 1 over 2c d mu a mu squared. This is a favorite gauge fixing term. And so we've got a c term in here. This introduces a new counterterm, so we'll have a counterterm of c. And that one will be used to modify p nu terms. In Feynman gauge, this thing is simpler, and this thing becomes simply minus I delta 3 p squared g mu nu. Now there's another term that will occur, namely a vertex correction, and we'll write that this way, and that will be minus IE delta 1 gamma mu, and that then comes from this term. So in other words, what we're doing now is we would be doing our Feynman rule using not just these four terms, but also these four terms. And these guys we could use to cancel the things that occur over there. All right. And so in particular, let's go to the electron propagator to see how this works. We have psi of x, psi bar of y. By the way, let me just mention something that's totally irrelevant to the course, but since some of you go to the NUPAC seminar, I said that I had a mistake in the paper I put on the archive, but I did it right in the NUPAC seminar. No, it's the opposite. The one on the archive was right, and I made a mistake in the NUPAC formula. It's that the determinant of the Jacobian, the absolute value of the Jacobian should be in the numerator, not the denominator. And if anybody wants a corrected version of the slides, send me an email, I'll send it to you. Okay, anyway, back to the electron propagator. Remember, this thing is shorthand for mean value in the vacuum of the time order product. And we're going to call this, we're going to say this is an integral d for p over 2 pi to the fourth, e to the minus I p x minus y. I wonder if Fourier had any idea how much use we would make of his insights. In fact, I think he had a hard time getting mathematicians to take seriously what he was doing. We know how to deal with mathematicians. I think actually Dirac had similar problems. IG of P slash. Okay, now IG tree of P slash. Notice I would have used 0 or 1 or something, but 0 is bare, so we have to use T for tree. And a tree means, well, it looks like a tree. Tree branches go like this. There aren't any loops in trees, and so that's the idea of a tree branch. This thing then is the lowest order tree graph. This is the tree graph is this, and it's I over P slash minus M plus I epsilon. Sometimes we're going to leave out the I epsilon, not for any reason, but just because we get tired. Now, there are corrections to this, or let us say, what is the one loop one? Well, the one loop one, there are two terms. There's this term, which we've computed in the past, and this is, we're going to write this as I over P slash minus M, I sigma 2 of P slash I over P slash minus M, and I've left out the I epsilons. But then we've got the terms that come from over here. In other words, that guy up there. And so this is going to give us I over P slash minus M, and that's just, we're including these external propagators. I P slash delta 2 minus delta M plus delta 2 M, and then I over P slash minus M. Okay. So we add these two together, and we add this one. So to order E squared, our IG of P slash is I over P slash minus M plus I over P slash minus M I sigma 2 of P slash plus P slash delta 2 minus delta M plus delta 2 M I over P slash minus M plus order e to the fourth and so forth. Okay. So this is our electron propagator at the one loop order, and we can imagine going beyond this. There isn't any other one particle irreducible diagram, but we can imagine summing the series of one particle irreducible ones. And so we'll write sigma of p slash as sigma 2 of p slash plus p slash delta 2 minus delta m plus delta 2 m plus other, I'll just write them this way, other one particle irreducible diagrams. Okay, so these are all order e to the fourth and higher. So we imagine, that's what we call sigma of p slash. So then what we can say is that the whole electron propagator then will be I over p slash minus m. And so I should say this, that what we're doing here is equals. This is I g of p slash equals I over p slash plus m minus m. I over p slash minus m, I sigma, I'll just write it as sigma, I over p slash minus m, plus I over p slash minus m, I sigma, I over p slash minus m, I sigma, I over p slash minus m, plus dot dot. And we can rewrite that as I over p slash minus m, sum n equals 0 to infinity, I sigma of p slash, I over p slash minus m, raised to the nth power. Okay. And now, what are we saying about this sigma? What we're saying about this sigma is that when you get sigma 2 and these counterterms, well, we can imagine sigma is actually very small because the infinities in sigma 2 are going to be canceled. Although, let us say the 1 over epsilon terms, the ones we're calling euphemistically 10. The 10 terms are canceled by these deltas. Okay, so this is actually something small. And so it actually makes sense then to do this, sum this geometric series, and then what we get, let me go up here. What we get is I over p slash minus m times 1 over 1 minus this, which is I sigma times 1 over p slash minus m. And now, if we multiply through, and let's keep in mind that sigma, okay, it's a matrix, but it's what? It's a linear combination of the identity and powers of p slash. So it commutes with p slash minus m. So there's no mystery here. We can just do ordinary, treat these as ordinary numbers. And then at that point, what we have is I over p slash minus m plus sigma of p slash. So that's our electron propagator. And now what do we want? Well, we want that when P is on the mass shell, in other words, when P squared equals m squared, Schwartz writes that as P slash equals m. I think that's just confusing. We want to say that when P is on the mass shell, this vanishes so that we get the normal electron propagator. And moreover, we know that this pole at P slash equal to m, there I said it, has residue I, not I times 1.3 or something. So we want that there shouldn't even be any term linear in P slash here. This thing here shouldn't have an extra P slash in it. So it shouldn't have a constant, shouldn't have a P slash. Okay. So what are these conditions? These conditions are sigma of P slash, which I think, which he writes it P slash equals M. Well, you might as well call that sigma of M equal to 0. I mean, it's just silly to say sigma of P slash equals M. I mean, it's sigma of M if you mean that. And so what I'll mean by this is just P is on the mashup. And then d by dP slash of sigma of P slash, and now here I guess one has to say P slash equals M. This should be 0. So what this really means is that sigma of P slash is A times P slash squared plus B times P slash 2 plus ... right? At least wait a minute, maybe I've got this wrong. I'm sorry, it's P slash minus M squared, P slash minus M cubed. Do I have this right now? Let's just think about it. Setting P slash equal to M course, we satisfy the first condition. Taking the derivative, yeah, we satisfy the second condition. So I think that's what it means. It means that as a power series in P slash minus M, the lowest order term is quadratic. Now, on the other hand, we have an expression to one loop order for what sigma P slash is. It's this thing here. And so the first condition, that sigma of M vanish, is the statement that sigma 2 of M plus M delta 2 minus delta M plus delta 2 times M, all that should vanish. Well, those two terms vanish, and this then just says that sigma 2 of M should equal M delta M. Sigma 2, right, because sigma has that thing canceled here. The other statement is that the derivative should vanish, and if we take the derivative, we get delta 2 here. So what we have is d sigma 2 dP slash at M plus delta 2 should vanish. So we have the delta 2 is equal to minus d by dP slash of sigma 2 at M. Any questions? Remember, I have candy. In fact, I should have given a piece to the TA. I'll
later
do that in a minute. Okay, so these are conditions. This is a condition on sigma on delta M, and another one on delta 2. Now let's find out what delta 2 is in dimensional regularization. Dimensional regularization, what this means is that delta 2 is going to be e squared over 8 pi squared minus 1 over epsilon minus a half log u tilde squared over m squared minus 5 halves minus log m gamma squared over m squared. Remember, this m gamma we put in to avoid an infrared singularity because we're not treating the soft photons correctly. In other words, we've got this, I mean, the fact is that low energy photons are very cheap. And so you're going to have them everywhere in these diagrams. And if you treat them properly, then you'll cancel the infrared divergence. In Pauli-Villar's, we have delta 2 is e squared over 8 pi squared minus a half log lambda squared over m squared minus 9 over 4 minus log m gamma squared over m squared. Okay. All right. Okay, so in other words, what we've got here is that we're computing this thing here. We've got the delta 2, the delta m, and so forth. And we want this thing to, this whole thing to vanish when P is on the mass shell. And so that tells us that that the delta 2 has to cancel whatever this thing is in dimensional regularization or Pauli-Villar's regularization. And so when we do that computation, we then find that delta 2 has to be either that or that in order to satisfy actually both conditions. I think both conditions get satisfied. Okay, now let's turn to the photon property. Here well, I might as well use up this board space here. Here we're talking about a mu of x, a nu of y, again, time ordered product, mean value in the vacuum. We again use Fourier's trick. What's a little puzzling though is that there was somehow a minus I there and a plus I here. So the sign of I actually the sign of the IP matters in the electron propagator because it's a fermion. It doesn't matter in the boson propagator. And I'm not going to try to track it down to see if it's a typo in Schwartz or not. There was a typo, by the way, in equation 19.1. The first psi should be psi log. It's kind of obvious. Right, yeah. Okay, so what are our diagrams here? Well, because as we know, we'll have this one, and then we have the one loop thing, which we computed last time, and then we're also going to have the counterterm piece. And so we're going to add up all three. And in particular, this guy is going to cancel the bad part of that. Or let us say, there's going to be some terms of order 10 here. This is also minus 10, and we're going to cancel. Okay, so what was this one loop thing that we did last time, or the time before, I don't remember now. Minus I, p squared, g mu nu minus p mu p nu. And we're going to write it as e squared pi 2 of p squared. And if we take that Lagrangian from the front board there, maybe turn that on. So we're going to use that thing to compute, let us say, this diagram as well as these two diagrams. What we're going to find is, well, first of all, in dimensional regularization, we're going to find that P2, pi 2 of P squared, at least this piece here, is 8 over 4 pi to the d over 2. Remember, d is 3.9 or so. Gamma of 2 minus d over 2. Mu, this is called a subtraction point. It's just some mass that we... Remember that fields have funny dimensions. Fields and coupling constants have funny dimensions if you're in a funny dimensional space. And so this is 4 minus d, integral 0 to 1 dx, x, 1 minus x, 1 over m squared minus p squared x, 1 minus x, to the 2 minus d over 2. Okay, so that's what this one loop diagram is. And so I think I misspoke before. I said we were including these guys, and we're not including them yet. We're just doing the one loop diagram. And there's going to be a term of order 10 here. And d is 3.9. Okay, well, if we do the integral and expand it, well, actually, we don't even do the integral. We just expand the gamma function and mu and d and so forth in power and about let's see, we expand about d equals 0 is what we do. And then what we get is 1 over 2 pi squared integral 0 to 1 dx, x, 1 minus x. We get 2 over epsilon, so this is about 20 now. Plus log mu tilde squared over m squared minus p squared x, 1 minus x, plus order epsilon. Okay, so that's what pi 2 of p squared is. And we want to cancel this term, which is of order 20. And we'll do that by using this term. And what is that term? Well, that term is minus I delta 3 times p squared g mu nu minus p mu p nu. And what Schwartz does now is he jumps to a different gauge. Instead of Feynman gauge, I forget what this gauge is called, but he wants to use a photon propagator that is proportional to a projection operator. And I mean, G mu nu is not a projection operator, but it's not all that different from a projection operator. I mean, diagonal, when you square it, you get, you know, regular repetitions and so forth. But anyway, let's follow what he did. So he's using this propagator now. Sometimes I'm going to write this as p squared, sometimes p. And so this is minus I g mu nu minus p mu p nu over p squared divided by p squared plus I epsilon. And I'm going to call this minus I p mu nu of p squared. And I'm going to drop the p squared, the other p squared pretty soon. P squared plus I epsilon. Now, what's nice about this is that p mu nu, big P mu nu, is g mu nu minus p mu p nu over p squared. And what's nice about that is that it's a projection operator, in the sense that if you have p mu alpha, say p alpha nu, Shall I work this out? Or you want to, all right, there was a nod. All right, so P mu alpha minus P mu P alpha over P squared times, so I'm going to ask you guys to help me because this is in my notes. I skipped this. This would be G alpha nu. G actually is eta. I'm sort of annoyed at Schwartz for using G when he should use eta. I mean, G is the thing that's, you know, occurs in general relativity. Eta is the flat space metric, but all right. Anyway, minus P alpha P nu over P squared. Okay, so let's multiply this out. The first term, what does this do? This thing just raises the alpha and makes it a mu. So this is just G mu nu. That times that, because we're summing over alpha. Summed over here, we get minus P mu P nu over P squared from these two guys. And now we do these two. Okay, so this one is minus P mu, and this thing just turns out, this thing is effectively delta nu alpha. This turns alpha into nu. And then we have this one, which will be P squared, canceling a P squared, and that'll be plus P mu P nu over P squared. So we had three P squares, 1, 2 in the denominator, and P alpha is P squared. Okay, so this guy cancels that guy, and this is P mu nu. Okay, so it's a projection operator in that sense. I think it, in all these calculations, it makes a great deal of sense to use upper and lower indices. And so this is explained in my book chapter. Anyways, the chapter on tensors where this is all.
Should be chapter 11.
Huh?
Should be chapter 11 on tensors.
Yeah.
Oh, yeah.
Okay. All right, so what's this? So this is the tree level thing. What happens if we include this diagram plus this diagram plus that diagram? I'm running out of blackboard space again. What we have is I G mu nu of P, let us say. So this is the propagator, the one loop, the counter term, and then we're imagining higher order terms. Okay. So what this is going to do is just the one loop order, it's going to give us this. Minus I, G mu nu minus P mu P nu over P squared divided by P squared plus I epsilon. And then these terms are going to give us 1 from that term, minus E squared pi 2 of P squared from this term, and then this term is going to give us minus delta 3. And then we've got plus order e to the 4th. Now we're going to define pi of P squared to be E squared pi 2 of P squared plus delta 3. Now notice what we've done here. By combining these two, we're going to be canceling the terms that are of order 10 or 20 or 30 or whatever. And so pi is this thing that's actually small. And we can also imagine that we've added the the 1 pi terms, which of course are higher order in E because there aren't any
the one loop level.
All right, so then, if we're going to be computing this I g mu nu of p, then we're going to say is the lowest order term 1 pi, 1 particle irreducible, 1 particle irreducible, plus dot dot dot. Well, this thing, what is it going to be? It's going to be minus I, my p mu nu, okay, over p squared, I'm leaving out the I epsilon, minus I p mu nu over p squared, and then minus pi times p squared, 1 over p squared, minus I p mu, well, it's p mu nu because, remember, the thing's a projection operator, so I'm not going to fuss with that. P mu nu over p squared, minus pi p squared, 1 over p squared, minus pi p squared, 1 over p squared, plus dot dot dot. And running out of blackboard, I'm going to use lower ranges here. This is then minus I p mu nu over p squared times the sum of minus pi times p squared divided by p squared. So in other words, it's this thing, this thing, this thing, to the n equals 0 to infinity. So the p squared terms cancel directly. And this then is minus I p mu nu over p squared times 1 over 1 plus pi. And that's 1 over p mu nu. Remember, p mu nu is that projection operator, divided by p squared plus p squared pi. And it's p squared pi to p squared, of course, so plus I epsilon, if you want to add that in also. Okay, so that's our photon propagator. And because we had some terms of order 10 or 20 or 30 here, but they were canceled by this guy, which is also minus 10 or minus 20, minus 30. So in other words, this whole 9 yards, this thing is then I g mu nu of p. It is going to be minus I g mu nu minus p nu over p squared, 1 over p squared times 1 plus pi of p squared plus I epsilon. All right, so that's our photon propagator. Now, in dimensional regularization, okay, well, I'm sorry, I skipped something. What do we want? We want pi of 0 to be 0, because we don't want to change the residue here. It's just the residue factor. Yeah, my notes are actually wrong here. Okay. Anyway, now what about dimensional regularization? Well, in order to have pi of p squared 0, what we have to have is the delta 3. In other words, what we got here is delta 3 is equal to minus e squared pi 2 of 0. And pi 2 is the thing that has factors of 10 or 20 in it. And so that's our condition. And now if this condition in dimensional regularization is minus e squared over 6 pi squared, 1 over epsilon, 10, minus e squared over 12 pi squared log u tilde squared over m squared. So that's the delta 3. And now, if we then, in dimensional regularization, set delta 3 equal to this, so that these terms of 10 or 20 cancel, what do we get as pi of p squared? We get e squared over 2 pi squared, integral 0 to 1 dx, x 1 minus x, log m squared over m squared minus p squared, x 1 minus x, plus order e to the fourth and so forth. Of course, this is exactly what we got from doing derivative analysis. On the other hand, as I said to you, I'm not sure how easy it is to turn that differentiation type regularization into a systematic procedure that does everything to all orders. But it is interesting we get exactly the same result. Okay, now let's go to the 3-point function. Not much board space left. We've got minus I e gamma mu. This thing we're going to define as photon in all one particle irreducible diagrams that have one photon line, one electron in, one electron out. And of course, it's the electron-positron line, basically. Okay, so this is minus I e gamma mu plus higher term. By setting this equal to the E that Coulomb saw, where that's going to be sort of a renormalization condition. Okay, now, back in a previous chapter, it was argued that gamma mu would have to be of this form. F1 of p squared gamma mu plus I sigma mu nu over 2me, mass of the electron. This m, of course, is me throughout. I dropped the e as well as the capital R. P nu F2 of p squared. And in order to have this the case, what we need, of course, is at tree level, F1 of p squared is 1, and F2 at tree level of p squared is just 0. So that reproduces that. All right, now I'm wondering about doing some erasing. Maybe when I do this erasing, you guys maybe have some questions. One question is, why did I erase this board rather than the one in front? Oh, well, there goes the Lagrangian. Well, we'll keep the rest of it. So that's maybe why it was good to erase that one. All right, let me first of all pay the TA. Sorry. All right, are there any questions while the board dries in the New Mexican air?
So F1 and F2, those are kind of like form factors?
Yes.
I have a question.
Okay, so this is the lowest order diagram, and we can imagine there are two corrections. So while the board is drawing, let me say what these things are. The extra terms, the diagrams, in other words, are first of all, of course, is this diagram, which gives us this. And then there's going to be the vertex correction where the photon goes across here. And then there's the counterterm correction, which just looks like this, but we write a star there because we're going to be subtracting terms of order 10 and 20. Okay, now, earlier we actually computed some of this, and in fact computed F2. It was an integral, it turned out to be an integral over dx, dy, dz, all from 0 to 1 with a delta function. This is due to a Feynman trick. And I'm waiting for this to dry. Maybe I'll use this part of the board up here. So F2 of p squared, this is what we found, okay? E squared over 4 pi squared integral 0 to 1 dx, dy, dz. Delta x plus y plus z minus 1. This is the Feynman trick, okay? You have three denominators, you combine them. Z1 minus z, m squared, and then we divide by 1 minus z squared times m squared minus xy p squared, and then plus order e to the fourth. And what we found was that that this was actually finite. This was a finite integral. And what we got was that F2 of 0 turned out to be simply alpha over 2 pi. And that gave us, you remember, the G minus 2, the correction to the magnetic moment of the electron was then 2F2 of 0, or alpha over pi. And all right, so that's that. Let's go back now to F1, which had a divergent piece. So in other words, when we write this thing as F1 gamma mu plus F2 sigma mu nu p nu, the F2 thing is non-singular, but there are terms of order 10 or 20 in the F1 piece. Okay, so we're going to say that F1 of p squared is, we're going to write it as F1 plus F of p squared plus delta 1 plus order e to the 4th. And the delta 1 comes from this term here. And that's the term that we represent diagrammatically as this term here. And so, what was f of p squared? Well, that turned out to be minus 2i e squared and integral d4k over 2 pi to the 4th, an integral dx, dy, dz, all from 0 to 1. Again, delta x plus I plus c minus 1. And all of that times inside the integrand, it's k squared minus 2, 1 minus x, 1 minus y, p squared minus 2, 1 minus 4z plus z squared. That's m squared, and then this whole thing is divided by a cube of k squared minus m squared 1 minus z squared plus xy p squared cubed. All right, so what we want, of course, is that gamma mu of 0 is just gamma mu. And so that means then that delta 1 should be minus f of 0. Because in other words, over here, we want f of 0 plus delta 1 to cancel. Right? Because we want f1 to be 1 when p is 0. P is the full momentum of the photon. All right. Now, if we do this integral in dimensional regularization, we then have f of c squared is minus 2i e squared mu to the 4 minus d integral d dk 2 pi to the 4th integral dx dy dz over from 0 to 1 delta x plus y plus z minus 1. And what's left is 2 minus 4 over d k squared minus 2 1 minus x 1 minus y p squared. Well, I mean, you can just read it off from that. Minus 2 1 minus 4z plus z squared m squared, and all that divided by k squared minus delta plus I epsilon cubed. And of course, the I epsilon we get rid of when we do the Wick rotation. And of the K0 integral. Delta here is 1 minus z squared m squared minus xy p squared plus z times m gamma squared. And again, this m gamma squared is the cheap way of treating soft photons. All right, now if we look at this integral, we can see that we've got 1 over k to the 6th, so we're really in pretty good shape. The only problem comes from the k squared term. And the k squared term is mu to the 4 minus d, an integral dd of k over 2 pi to the 4th 2 minus 4 over d k squared over k squared minus delta plus I epsilon cubed. And now rotating into doing the Wick rotation and then evaluating the integral once it's easily done, and we're doing it, remember, we're using these various gamma function identities to do these rather weird integrals. What we get is mu to the 4 minus d I over 4 pi to the d over 2, 2 minus 4 over d over 4, gamma of 4 minus d over 2, and setting epsilon equal to 4 minus d, we get I over 16 pi squared, 2 over epsilon plus log mu tilde squared over delta minus 1 plus order epsilon. Okay, so let's see. This is somehow skipped something in my notes. I guess the point is that once we've isolated the k integration, The rest of the integral involves just these things. And consequently, we finally find that f of p squared is e squared over 8 pi squared, 1 over epsilon minus a half plus an integral 0 to 1 dx dy dz delta x plus y plus z minus 1, and that's times p squared 1 minus x 1 minus y over delta, but there's also a term m squared 1 minus 4z plus z squared, and then finally log mu tilde squared over delta. So this is what f of p squared finally is, and what we see is we've got f1 is 1 plus f of p squared in delta 1. So there's a term in f of p squared of order 10. We're going to cancel that with a delta 1. And what we do then is we say in particular that f of 0 then is e squared over 8 pi squared, and this turns out to be 1 over epsilon plus a half log mu tilde squared over m squared plus 5 halves plus log m gamma squared over m squared. So that's what f of 0 is, and it has to be minus delta 1. And now this is in, of course, dimensional regularization. Now if we compare our formula for delta 1 with our formula for delta 2, does anybody see it? Where is it? I probably, oh, here it is. Delta 2.
Yeah.
Right there. There it is, yeah. You can see that the formula for delta 1 and the formula for delta 2 are the same. In fact, one can prove that they're the same for all orders of perturbation. That's a remarkable process. And it means that the electromagnetic current does not get renormalized. The renormalization of the charge, I guess, cancels the renormalization of the electromagnetic of the fermions. Anyway, so we've seen that they're the same. Delta 1 equals delta 2 in dimensional regularization. If we had done Pauli the laws in detail, we also would have found delta 1 equals delta 2. Okay, so what we've got here is then 4 renormalization conditions, which I guess I can write here. We've got sigma of m is equal to 0. Sigma prime of m equals 0. M just means that p is on the mesh. We've got that big gamma of 0 is ordinary gamma, and the big pi of 0 is 0. These are the 4 conditions, and these conditions we've used at the e squared level, where e squared over 4 pi is 1 over 137, to fix the 4 counterterms, delta 1, delta 2, delta 3, and I guess delta E. And now we can go on to higher levels and higher orders, and we would still maintain these conditions. It's just that people who are doing that are doing these calculations to higher orders and loops. And this whole business of canceling these factors of 1 over epsilon, you can continue to do it. And So are there any questions, or should we just stop here? All right, let's stop here.